I'm Mr. Ish and I'm welcoming you to this video. When you're looking here at this particular concept of velocity and time graphs, how can you analyze these type of graphs with regards to acceleration? And that's the topic for this video. Thank you for joining me. We have a graph over here with time as the x-axis independent variable, velocity is your y-axis dependent variable, and you can see there's a bunch of lines and there's a curve. If we are going to look at everything here with regards to acceleration, then break everything down into time intervals, and it is 0 to 5, 5 to 10, 10 to 15, 15 to 20. When you focus in on the first time interval of 0 to 5, that's this interval here, you can see you have a horizontal line. Now, when you have these type of graphs, if you're simply reading off the graph, you're getting two pieces of information, that's your velocity and time. When you simply read off the graph without any analysis, you're getting only velocity and time. If you're going to do any kind of slope determinations, then you'll get your acceleration data. So keep that in mind. When we look here at the 0 to 5, we have a horizontal line. Slope is equal to 0, which means we have a constant velocity. And there can be only acceleration when there's a change in velocity over a change in time. If the velocity does not change, there can be no acceleration. Coming back over here, we have a horizontal line, slope is equal to 0. There is no change in velocity, therefore there is no acceleration, but there is indeed velocity, and you simply read off the graph, it's 10 meters per second, and the object is going to be moving, because if there's a velocity occurring, the object must be moving. So that's what we see from right here. Now let's focus at this 10 to 15 second time interval, which is right over here. Again, we have a horizontal line, slope is 0, so acceleration will not be present. But simply read off the graph and you're seeing that the velocity here is equal to 0 meters per second. Therefore, the object must be at rest. And there is obviously no movement. So you can see here, two time intervals here are only looking with regards to velocity and some sort of movement or no movement, but there is indeed no acceleration over here, which means there are two time intervals, this interval here and this interval here, where it seems like velocity is changing and where you will have acceleration. So now in the remainder of this video, we will analyze that. When we look at this 5 to 10 second interval, what do we see? We're seeing that the line has changed. There's a certain inclination to this line, or an opposite of inclination. It's not inclining upwards, it's declining downwards. So you can say it's having a slope but downwards. But since you have this kind of a line, you know you can have a change in velocity, there will be acceleration. But simply reading off the graph, if you look at any of these intermediate seconds, you would just look across, those will give you your velocities at that time. Here you might have a velocity of, let's say, 8 meters per second. Here you might have a velocity of 6, here 4, here 2 meters. So you know you're seeing indeed a changing velocity. Because you have a change in velocity, you'll have acceleration. But how do you determine acceleration? Just do your basic slope analysis. You have a point 5 comma 10. That's this point right here. You have a point here 10 comma 0. When you do your slope, you're getting 0 minus 10, which is a minus 10, and 10 minus 5, which is a 5. You have a minus 2 meters per second square. Since you have a straight line, you have acceleration, but you have constant, or you can say uniform or steady acceleration in each of the time intervals, 6 seconds, 7, 8, 9, 10. You'll have this constant uniform acceleration of minus 2 meters per second square, but you will certainly have changing velocity. You would simply read off the graph. Along the y-axis, you'll see 9, 8, 7, 6, 5, 4, 3, 2, 1, 0 meters per second, and obviously the object is moving, but the object is slowing down and it's going to come to a rest, which is why here we have 0 velocity, 0 movement, and 0 acceleration. But this time interval has been analyzed. You simply read off the graph, that will give you your changing velocity. You do your slope analysis, that's giving you your acceleration factor. Because you have a straight line, you have uniform or steady acceleration in each of the seconds of that time interval. When you look at this last time interval, 15 to 20 seconds, now a bit of work is needed, because what you see over here is if you were to extend this upwards, you have a parabola. Now you have to determine the equation of this parabola, because if you want to start determining acceleration, you have to do derivative analysis. Because you do not have a straight line here, you have a non-linear function, you're going to have a changing acceleration and a changing velocity for each of the seconds which are involved. You would simply again read off the graph to get your velocity, but you would have to do derivative analysis to get your acceleration, but acceleration will not be the same in each of those seconds of this interval. How can we determine the equation? Well, I know I have a vertex over here at 15, 0, and I know I have a point over here which is 20, 20. I'm looking at a function which is f of x, or since we're doing an equation here, we are looking really here at a velocity function. Velocity with regards to time will be a times t minus h whole square plus k. This is the standard form of a parabola adjusted for these new variables of time and velocity instead of x and y. I have all of the items I need to make this equation. I have velocity with respect to time is equal to a times t minus h. I have here a t value, I have here a v value, I have here an h value and a k value. T 20 minus h 15 whole square plus 0, which is meaningless. All of this is equal to what? This value right here, 20. You have 20 here is equal to a into 25, and then a is equal to 4 over 5. So my velocity function becomes this. I have a 4 over 5 times t minus 15 whole square, and that's my function. This function, if I do the derivative of this, I'm going to get my acceleration function. You can do the chain rule. When you simply do the chain rule, it's not hard. You're getting a 4 over 5 times d over du, u square, and then du over dt, t minus 15. From all of here, you're getting a 1, but you're getting a 2u times 4 over 5. You're getting here an 8 divided by 5 times t minus 15. That right here is my acceleration function, 8 divided by 5 times t minus 15. And we are good. Just remember again, when we determine the equation of this nonlinear function, you want to call it, you're getting a velocity function. When you're doing the derivative of that, you're getting your acceleration function. And that's something you should know, because the derivative will give you your instantaneous rate of change, which is basically your slope of your tangent lines you can create off of that curve. Now we know the object is certainly moving because we don't have a velocity here, it's 0. You don't have that. You have a velocity which is changing. You would simply just look across and you get your velocities. We know there is a changing velocity for sure because it's a nonlinear line and it's not a flat line with a slope 0. And we also know we have a changing acceleration. And now let's look at this acceleration. In the time of 15 seconds, you would simply look right over here and start plugging in away. You'd have a 15 minus 15, which is a 0 times that. At the time of 15 seconds, you have a 0 meters per second square, and it makes sense. You're at the vertex of a parabola where a horizontal tangent line would be seen. The slope of that tangent line would be 0. Now as the object starts moving, you're looking at time interval 16. You're looking at the time 16. You put 16 in here. In this 16 minus 15 is a 1. You're getting an 8 over 5 meters per second square. At time 17, you put it in here. You're getting a 16 over 5 meters per second square. And you see everything is going by 8/5. In time 18 seconds, you're going to be having 24 over 5 meters per second square. And at time 19, you know it's going to be 32 over 5 meters per second square. But you can see in each of the seconds of this time interval, because you have a nonlinear function, you have non-uniform, and that's the word you want to learn, non-uniform acceleration, and that's exactly what it is. And obviously in the time 20, you can have 40 over 5 meters per second square. You put 20 in here, and you do 20 minus 15 is a 5. 5 times 8 is 40. 40 divided by 5, and that's exactly what you see. So keep in mind, in this time interval, there's a lot going on. The object is moving. The velocity is changing. How can you determine the velocity? Simply look across and read your graph. As I've told you, when you simply read off your graph, you're getting velocity and time. That's it. But when you do the slope analysis, you're getting acceleration. You have changing acceleration. It's non-uniform, and that's exactly what it is. You have a different acceleration value for each of the time seconds that is involved, and you know those acceleration values represent the slope of the tangent lines at each of those seconds, and that's exactly what it is. And that brings us to the end of this video. Thank you. Have a good day. Bye.